welcome to this video on the CIE exam, and this is paper 2. So this is all the structured questions for AS level. This is the core, and the exam code for this, if you're looking for this exam, the one we're going to look through is 9701/22, and this was the May or June 2014 paper. So the whole point of this video is basically to go through the questions and to make sure that you know how to answer them. But crucially, the most important thing is I'm actually going to explain why it's the answer as well, and go through worked examples, because I know the mark scheme will obviously tell the answers, but it doesn't necessarily tell you why it's the answer as well. So that's the whole point of this video. As you can see on the left hand side, you can see some links. If you click on the links, you can skip to a specific question. So if you don't want to do question 1, you can skip to question 3, and so that may help you as well. Okay, so let's make a start. Okay, so this is question 1, and question 1 starts by asking, explain what is meant by the term nucleon number. So the nucleon number is the total number of protons and neutrons. So that's just something that you need to know, really. So we'll put that on there. So total number of protons and neutrons. So that's just one mark. That's one that you really do need to know. Okay, so part B, it says bromine exists naturally as a mixture of two stable isotopes, bromine 79 and bromine 81, with relative isotopic masses of 78.92 and 80.92 respectively. So it's define the term relative atomic mass. Okay, so this is again another definition. A relative atomic mass is something where we take the mass of an atom or an isotope and we measure it relative to carbon-12, or 1/12 of the mass of carbon-12. And carbon-12 is like our reference element in the whole periodic table, and everything is measured relative to it. So it's 2 marks, so we need 2 points really. So the first one we're going to put is the mass of an atom, or you can say isotope, either or, relative to, and this is going to be 1/12 of the mass of carbon-12. There you go. Okay, so you get 2 marks for that. So the marks come in by first mark by saying the mass of an atom or an isotope, and then it's relative to 1/12 of the mass of carbon-12 gets to the second mark there. So there's 2 parts to that bit. Okay, and then part 2, it's for 3 marks. So he's using the relative atomic mass of bromine, which is 79.90, calculate the relative isotopic abundance of bromine 79 and bromine 81. Okay, right. So what we have to do, I'm going to write out our 2 isotopes just here at the top. So this is going to be 79 Br, and we've got 81 Br. Okay, so the first thing we need to do is to actually work out the isotopes, or how we work out the mass of the isotopes. And to do that, we need a periodic table. So just bring in a periodic table here. Okay, so we can see that this is the bromine 79, and if we come back up to here, it just tells you, so if I just show you here, so this tells you that we have the 2 isotopes here, which is 79 bromine and 81 bromine, as a relative isotopic mass of 78.92 and 80.92 respectively. So these are the isotopic masses that we're going to use for this answer here. So I'm just going to drag that up there, and just so you can see it. Okay, so we've got 78.92, so this is the relative isotopic mass, and to work out effectively the abundance of this isotope, remember we take the isotopic mass and normally multiply it by the abundance, and we do the same for this isotope as well, and then divide it by the total. In this case its percentage will be 100, and that will give us the relative mass of bromine, but because we have the relative mass, we have to work backwards. So there's a bit of algebra involved in here. So we're going to have 78.92. I'm going to put x on the end there, and the x shows us this is multiplied by the abundance, but we don't know the abundance of this. And then likewise for this as well. This one was 80.92, and this time we're going to multiply this by 100 minus x. That's basically the total abundance has to be 100 because it's percentage abundance, minus whatever the abundance is of this, and this will tell us the abundance of isotope 81. So it's just whatever's left, effectively. That's what that little bit means. And then in comes the algebra bit. So what we're going to do is we're going to write our expression out here. So it's going to be 78.92x. And we're going to add that to the relative isotopic mass of this element, this isotope. That's going to be multiplied by 100 minus x. And all of that is going to be divided by the whole thing. It's going to be divided by 100 because that's what the whole thing's out of. And all of this is going to equal 79.9. So this is the relative atomic mass. Normally what you do is you'd have this number and have this number, and then you work out this number. But we're doing it backwards here because we're working out the relative abundance. Okay, so then what we have to do is we have to try and expand these brackets here. So I'm going to rewrite this bit here. I'm going to rewrite this bit out. So we'll do it in stages so you can see exactly what's going on. 78.92 plus, right, now this is where we're going to multiply that by that to get rid of that bracket. So that's going to be 8092. Go. We're going to multiply this by minus x. So that's going to be minus 80.92x. Okay. So that's going to be that one. And then what we can do is we can then rearrange this, or simplify this, should I say. We can subtract, obviously, the x's. We've got 78.92x there and minus 80.92x. So if we I'm just going to write it over here. So if I take the 8092, and we're going to effectively, that's going to leave us with, if we take 78.92 minus 80.92, that's going to leave us with minus 2x, which is going to go there. And that's going to be divided by 100, that whole lot. And that's going to equal 79.9, as we know. And then what we have to do is we then need to get rid of, because we want x on its own, that's what we want to work out. So we're going to multiply this side by 100 and multiply that side by 100, because we're going to try and get rid of this 100 here. So we're going to bring it down here and just show you how we're going to do that. So that's going to be effectively, it's going to be 8092 minus 2x is going to equal, now that's going to be multiplied by 100, so that's going to be 7990, which is going to be that bit there. And so therefore, if I bring this bit across over to here and then move this x over here, then effectively what we have, let's bring that over there. So we're going to do 8092, and we're going to subtract that away from this, because if we bring this across, that's going to be minus. So that's going to be 7990, and that's going to give us 102. So 102 is worth 2x, or we'll just put 2x equals 102. So that means x would equal 51. So now we know that x equals 51. What we can then say is then we have to put it back into our ratio. So we have to calculate the relative isotopic abundance. So I'm just going to put our ratio, just going to squeeze it in here. So we have our ratio is effectively bromine 79. Let's hope we can fit it in here. We should be able to. 81 bromine. So our ratio should be 51, which is bromine 79, to 49, which is bromine 81. And there is your final answer. So what I've done, I've split this up. I've broken it up quite a lot. I'm sure those people who are pretty swift at math can think of obviously a lot quicker ways, but I've just shown this like this just to show you how it's worked out for those people who are maybe not so sure on how to work out these things. So because it is a bit of algebra. So you get 1 mark for this answer here. You get 1 mark for working out that x is 51, and then your final mark comes in for your ratio. So you get 3 marks in total there. Okay, right, question C, or part C. It says bromine reacts with the element A to form a compound with an empirical formula ABr3. The percentage composition by mass of ABr3 is A is 4.31 and bromine is 95.69. It says calculate the relative atomic mass AR of A and give your answer to 3 significant figures. All right, okay, so again, there's more maths here. This one's quite tricky actually. We've got quite a bit going on here, and we need to know how to effectively divide fractions in this one. So we're just going to put A on there, and we're going to put BR there, because we're looking at our ratio between A and BR. Now, normally, if you were working out the empirical formula, you would take the mass and divide it by the atomic mass. So that's what we're going to do here. Now, we know that mass of AR is 4.31. So we're going to put, this is a percentage mass. So, but we can just treat it like a mass. So it's 4.31 divided by AR, because we don't know what the atomic mass is for that. But for bromine, we do. So we're going to put 95.69, and we're going to divide that by the atomic mass of bromine, which if you use your periodic table, is 79.9. So that's the atomic mass of bromine, as you can see. So that's what we've done there. Now this is in a 1:3 ratio, this whole thing. And so we know the 3 part is actually linked with the bromine, because we can see it's Br3. So this bit is linked with the bromine, and this bit is linked with the A bit, which is the 1 bit. Now this is going to be very important, because now what we need to do is we need to put this into some kind of equation. So how we're going to do this is we're going to turn this into, instead of there, we're going to turn this into a divide. But we want to try and get rid of this 1 part. So I'll show you how we do this. So I'm going to just draw it over here. So we're going to do 95.69, and that's going to be divided by your 79.9, which is going to be there. And we're going to divide that by 4.31, and we're going to divide that by the AR. So effectively, we're dividing these two here. Now the reason why, and we're going to equal that to 3, because if this, remember this bit here was the 3 part, this was the bromine, remember that was part 3. So if we do 3 divided by, and this is 1, which is that will equal 3. And now what we've got is some kind of formula where we can at least aim to work out AR. So that's why we've worked it out there. Now, those of you who may remember these little bits of GCSE maths, you'll probably remember that when you divide 2 fractions together, then in fact what you do is you invert this fraction, flip this one upside down, and turn that into a times. So that's exactly what we're going to do. I'm going to write this down here, just where we've got a little bit of space. So we've got 95.69 divided by 79.9, and then I'm going to turn that into a times, and I'm going to put AR on the top, divided by 4.31, and that will equal 3. Okay, so that's what we've done there. And so then what we need to do is then, once we've done that, we just need to multiply the bottom 2 numbers together, and we're going to multiply the top numbers together and equal it all to 3. So we're going to simplify this fraction. So the top number is pretty easy. That's just going to be 95.69 times by the AR. We're going to divide that by, and these 2 numbers here. So we're going to do 79.9, multiply that by 4.31, and that should give us 344.369. So just put that in there, 344.369, and that's going to equal 3. Then what we do is we then, you can see we've got divide by 344.369, so we're going to multiply this side by that number and multiply that side by the same number to basically get rid of this. So we're trying to simplify here. So I'm just going to draw it up here. So if we do 95.69 times by the AR will equal, it's going to be 3 times this number here. So there's our number already in the calculator. I'm going to multiply that one by 3, and we should get 1033.107. Okay, so we're just going to put that there. 1033.107. Okay, and then what we need to do is we need to try and get the AR on its own. So we need to divide this side by 95.69. So if we divide that side by that number, we effectively cancel it out there, and we do the same here. So we're going to divide that by 95.69, and that'll tell us what the AR is. So we're going to take that number. The number's already in there from the previous one. So we're going to divide that by 95.69, and there we go, 10.796. But remember, we have to give that to 3 significant figures. So that's going to be 1, 2, and then 3. The number afterwards is a 9, so that rounds that up to an 8, so it's 10.8. So, and that is going to be our answer. And there we go. So that one's really tricky because you have to obviously use your math skills and how to use a fraction. But you can see the math is not too bad. It is just ratio and fractions. So if you don't like them, well then you might have to practice them, I think. So the marks, you get 1 mark actually for writing in 3 significant figures. You get 1 mark for your answer. So I'll put 3SF there. 1 mark for your answer, and you get 1 mark for actually drawing this ratio correctly here. So making sure that you've drawn this with your 3 there. So you get 3 marks in total for that one. So yeah, pretty tough question actually. Okay, right. And then on to the next part. So this is section question D. So the elements in period 3 of the periodic table show different behaviours in their reactions with oxygen. Describe what you would see with separate samples of magnesium and sulfur or reacted with oxygen, and you've got to write an equation for each reaction. Okay, so for magnesium, when you burn magnesium, you get this brilliant white flame, really bright, and you shouldn't stare at it directly actually because it's so bright. So I'm going to put this on here, bright white light. That's what you should get. And the equation, right, so the equation is going to react magnesium, and it's going to react with oxygen, and it's going to form magnesium oxide. MgO. This is going to be half molar to make sure it all balances. So there's your first one. And then sulfur. Sulfur is really nice. You get this really vibrant blue flame when you burn sulfur. So we're just going to put that in there. Blue flame. Yeah, have a look for it in YouTube. It looks really nice actually. You could also put white fumes as well. Because actually when you burn white misty fumes, so when you burn sulfur, you produce sulfur dioxide, which is a white, very choking gas. So we're going to write the equation here, sulfur plus oxygen, and that will just form sulfur dioxide. So that's probably the easiest equation in the world, that one there. You get 4 marks for this. You can probably see where they turn up. 1 there, 1 there, 1 there, and 1 there. So there you go. Okay, right. So on to part 3. I should have said part 2. Right. So it says write equations for the reactions of aluminium oxide, Al2O3, with sodium hydroxide. Okay, so sodium hydroxide is going to be the equation for this is Al2O3. So I'm just going to write that in there. Okay, that's Al2O3, and that is going to react with your sodium hydroxide. So we're going to put there sodium hydroxide, and this is going to produce, I'm going to have to react this with water as well, and this is going to produce this compound here, which is NaAl. This is going to be OH4 H2O2. Now this is what we call a complex. So you've got your aluminium in the middle, and you've got your sodium that's like attached to it ionically, and then what we have is our 4 OH or 4 OH groups surrounded it, and 2 water ligands that's left. So in terms of balancing, you would need 2 lots of this and 7 lots of water to make sure that the whole thing balances with the 2 there as well. And so that's going to make it balance. There's other varieties of this equation, so you need to make sure that you're getting the obviously the right one as well. Okay, and hydrochloric acid is Al2O3. This is your aluminium oxide, and we're going to react this with hydrochloric acid, and this is going to form AlCl3, aluminium chloride, plus water. So these really are equations that you need to know, how they well, you just need to know the equations really. Balancing, obviously we've got 2 aluminiums there, so we need 2 there. That gives us 6 chlorines, so we need a 6 there, and the hydrogens we need 3 there. to make sure that all balances. So there's your equation there for aluminium. Okay, and then E. Okay, so we've got phosphorus. Let's just move that over there. Okay, so we've got phosphorus reacts with chlorine to form PCl5. State the shape of and two different bond angles in a molecule of PCl5. Okay, so the shape of this PCl5 is phosphorus with 5 chlorines. It's trigonal bipyramidal. Okay, and the reason why, if I draw phosphorus, phosphorus is in group 5, so there's 5 electrons in its outer shell. If it's bonded with 5 chlorines, each electron has been involved with the phosphorus 5 times. So you're going to get this kind of square plane, this kind of trigonal plane a bit in the middle, and then your 2 axial there. So this is trigonal bipyramidal. And the angles here is going to be 120 degrees. And between here and here is going to be 90. So you're going to have 2 angles that's made up here. So this is going to be 120 and 90 degrees. And you obviously get 2 marks for that, 1 there and 1 there. And that's it. Right, on to question 2. Okay, so this is question 2. Question 2 says a 6.30 gram sample of hydrated ethane dioic acid. So it's H2C2O4.XH2O was dissolved in water and the solution was made up to 250 centimeters cubed. A 25 centimeter cubed sample of this solution was acidified and titrated with 0.1 moles per dm cubed potassium manganate solution. 20 centimeters cubed of this potassium manganate 7 solution was required to react fully with the ethane dioate ions, which are the C2O4 2- present in the sample. The MnO4- ions in the potassium manganate 7 oxidize the ethane dioate ions. Right, so we need to explain in terms of electron transfer the meaning of the term oxidize in the sentence above. Right, so you might remember the acronym, which is Allery. Oxidation is the loss of electrons, reduction is the gain. So in this case, what is losing the electrons is C2O4, because that says it's oxidizing it. So the C2O4, they lose electrons. All right, okay, so you just have to remember that one. Right, it says complete and balance the ionic equation for the reaction between manganate 7 ions and the ethane dioate ions. Right, so the first thing we need to do is look at the equation. You can see we've got a gap here. We need to put a number here and a number here. So some kind of reagent would go here. So what's going to go here is manganese, because you can see that's not on there. So this would be Mn2+. That's what it's going to reduce down to. And the number in front of that is going to have to be a 2 because we have 2 over here. So that's the first thing that we have to do. And then we need to look at trying to balance our oxygens here. Now you can see here we've got 20 oxygens here on this side for this molecule here. We have one here, but we'll put a number here to try and balance that. So we'll leave that for the time being. And the number of oxygens on this side is fixed. So we've got 5 times 4, which is 20 oxygens there. And we also have 2 lots of 4 oxygens there, so it's going to be 8 oxygens. So we're 8 oxygens short on this side. So that has to be an 8 on that side for that to work. And then we look at the number of protons, because we need to put a number here. And you can see here that we've got 2 8s, which is 16 hydrogens on this side. So we need 16 on this side to balance that. So that's going to be 16 that's going to go in there. You get 3 marks for this, and the marks come in pretty simply. You get 1 for this, 1 for that, and 1 for that to get 3 marks. So it's not too bad. Okay, and then B part 1. Calculate the number of moles of manganate 7 used in the titration. So the number of moles is going to be the volume, and the volume we said was 20 centimeters cubed, and the concentration was 0.1 moles per dm cubed of this was used. So to calculate the number of moles, it's just the volume times by the concentration, divide that by 1,000. And so if we put that into our calculator, let's just nudge that over there. So that's going to be 20 times by 0.100, press the equals, divide that by 1,000, and we're going to get 2 times 10 to the minus 3. So that's going to go in there. Okay, and that's going to be moles. Okay, and then part 2. So part 2 says use the equation in A part 2 and your answer to B part 1 to calculate the number of moles of C2O42- present in the 25 centimeter cubed sample of the solution used. Right. Okay, so what we need to do is we need to use the molar ratio in this equation here. And what we can see from that is actually the amount of manganate ions, MnO4-, to C2O4, so ether diurate ions, which is 2-. That's in a ratio of 2 to 5. Okay, there you go. And then what we need to do is obviously then we need to work out the number of moles. So in that ratio, one of the ways in which you can do that is you can just do 2.00 times by 10 to the minus 3, divide that by 2, and that's going to get us 1.00 times by 10 to the minus 3, because just halving that. And then we're going to take this number, this is for 1 mole, and we're going to multiply it by 5. So we divide it by 2 to find 1 mole, multiply by 5 to get the 5 moles, which is your ethane diurate. And again, that's just going to be 5.00 times by 10 to the minus 3. So we get 1 mark for that one as well. Okay, and then on to the next one. So it's calculate the number of moles of this salt here. This is your hydrated ethane diuric acid in 6.3 grams of the compound. Right, so we started with, remember this mole here, this number here, is the number of moles in 25 centimeter cubed solution. But right at the start, it said that we made a solution, the original solution was 250 centimeters cubed. So what we have to do is take this is the number of moles in 25 centimeters cubed. So we times this number by 10 to get it to 250 centimeters cubed, because 25 times 10 is 250. So we're going to take that number there, 5.00, times by 10 to the minus 3, multiply that by 10, and obviously that's going to get us 0.05 moles, or you can say 5 times 10 to the minus 2, so anything like that. Okay, so that's that one. And then it says calculate the relative formula mass of H2C2O4.xH2O. Okay, so the relative formula mass, we have the number of moles, and we also have the mass that was used originally, and it said 6.30 gram. So you can remember from your equations that mole equals mass over mR. So the mR, which is the formula mass, is effectively the mass over moles. So the mass is 6.30 grams, and we're going to divide that by the moles. And the moles we just worked out here is 0.05. Let's bring in the calculator. So we're going to do 6.30, and we're going to divide that by 0.05, and we're going to get 126. So there's our relative formula mass of this salt here. And then onto the last one. It says the relative formula mass of anhydrous ethane dioic acid, H2C2O4, is 90. Calculate the value of X in this salt, hydrated salt. So this is the relative formula mass of this. They've also told us the anhydrous version, so this is without the water. So what we're going to do is we're going to do 126, and we're going to minus that from 90. And so that's going to be 36. And so this is the mass of water that's left behind. And so to work out how many waters we've got, we just do 36, divide that by the MR of water, which is 18, and that will give us 2, because there's 2 18s and 36. So we can say X will equal 2. And that is quite simply how you work out the .xH2O bit. So there we go. That's the end of question 2. So that was 9 marks. On to question 3. Okay, so this is question 3. Question 3 starts by saying the elements in period 3 of the periodic table show variations in their behavior across the period. The bar chart shows the variation of melting points of the elements across period 3. Since here we've got melting point in Kelvin and we've got all the elements here. says in each of the following parts of the question, you should clearly identify the interactions involved and, where appropriate, explain their relative magnitudes. Right, so that's pretty important. And it says explain the general increase in melting point from sodium to aluminium. Okay, so sodium to aluminium is all metallic bonding, and as we go across the this period, the strength of the metallic bond increases, and this is because we have a bigger ion. The metal ion gets bigger. Well, the charge of the metal ion gets bigger. The actual size of the ion gets smaller. So because we have that, then that means we have an increase in charge density, and so therefore the attraction between the electrons, the delocalized state of electrons, and the positive charge is therefore stronger. So we just need to write this down into some kind of answer. So the first thing we need to say is that we have metallic bonding, because we need to identify the type of bonding, and the strength of metallic bonding, strength of the metallic bond increases due to increasing cation charge, or we can say charge density. There you go. Right, so it's pretty straightforward. It's 3 marks, so you get quite a bit of marks for this. You get 1 for talking about metallic bonding, 1 for saying that actually this increases as we go across the period, and 1 mark for explaining why that is the case. And this is because the increase in cation charge or the charge density increases. So that's quite important. Okay, so on to the next bit. So it says explain the variation of melting points from P to AR. Okay, so we have a big significant variation, and that is with sulfur, as you can see here. Sulfur is a little bit higher than the rest of them. So we need to say really what's causing this is sulfur is S8, phosphorus exists as P4, chlorine is Cl2, and AR is just on its own. So because this actually has the molecule of sulfur has more sulfur atoms in it, it therefore has more electrons. And because it has, and as a result, because it has more electrons, it has increased van der Waals forces. And so this gives it a slightly higher melting point than the rest of them. So let's write down our answer. So this is going to be van der Waals forces is greatest in sulfur. Okay, and we need to say that we need to give the reason as well. So this is, if I can spell, this is because it has the greatest number of electrons. Okay, so 3 marks. Again, they come in for 1 for saying the forces, 1 for saying that it's greater in sulfur, and this is because it has the greater number of electrons. Remember, it's electrons that are create the van der Waals forces. The more electrons we have, the stronger the van der Waals force. Okay, right. So part 3. So explain why Si has a much higher melting point than any of the other elements in the period. Now, silicon is significantly bigger compared to the rest of them. The reason why is to do with this structure. Silicon forms a giant covalent structure. So we're going to put that there. And that giant covalent structure gives it that significantly higher melting point. So that's pretty important. Okay, right, on to the next one. Okay, so this is B. Let's drag this down there. There we go. Right, so the graph below shows the variation of the first ionization energies across period 3. And you can see here we've got the first ionization energies, and then it's asking us some questions about these elements across period 3. So it says, explain why the first ionization energy of argon is greater than that of chlorine. Right, so what we need to say that argon has more protons in the nucleus, so that gives it an increased nuclear charge. But crucially, the shielding is the same in both chlorine and argon. So that increased nuclear charge, but the same shielding, means that the electron is much, much more difficult to extract from or to remove from argon than it is from chlorine for that reason. So we need to really, you've got to remember to talk about the shielding as well. It's quite often missed off. So nuclear charge is greater in argon, and they have the same shielding. Okay, so don't forget that bit there. Very, very, very important. Okay, right. And the next one, explain why the first ionization energy of aluminium is less than that of magnesium. So there's aluminium. And so why is it less than that of magnesium? Well, you can see here, this is the s orbital here, and then when we get to here, this is the p orbital, which is slightly further away from the nucleus than the s orbital. So therefore, this orbital here, the s orbital, is shielding the p orbital electrons, which are the rest of them up here. So that's what we need to say on there. And because of the shielding, it drops just slightly, just gradually. It's not a massive difference. So we can either say that the p subshell, or we can say orbital, is more shielded. Or we can say that the p subshell has a higher energy, because it is slightly higher in energy than the s subshell here. So that's why it's a little bit easier to remove that electron there. Okay, and then the last bit says explain why the first ionization energy of S is less than that of P. Okay, so if I just bring this graph back down again, just a fraction. So there's your sulfur and there's your P there. You can see it's just gradually declined a little bit. So it's just fractionally easier to remove an electron from sulfur than it is from P. At this point, remember your P orbital is like 3 blocks. So if I just fill this up like that. So you have 3 blocks in there. So aluminium, you fill up the first one. Silicon, the electron sits in the second one, and phosphorus sits in the third one. When we get to sulfur, we have to occupy, the next electron has to occupy this block here. There is a little bit of repulsion between this here. This electron doesn't really want to be next to this one here. So because of this repulsion, it's actually easier to lose this electron. Therefore, the ionization is slightly lower in sulfur than it is in the previous element. So that's what we need to put. So we'll write that in there. We have repulsion due to electron pair in the same orbital. And there we have it. So you get 10 marks for this question. So on to question 4. Okay, so this is question 4. Question 4 says crude oil is processed to give a wide variety of hydrocarbons. 4A, give the names of one physical process and one chemical process carried out during the processing of crude oil. Okay, so the physical process, when we are separating this, the physical process is obviously looking at the melting and boiling points. So the thing to do with, or the process requires, or the process in which needs melting boiling points or uses melting boiling points is fractional distillation. So because you have a fractionating column, so we'll put that there. Fractional distillation. There you go. Right. And the chemical process, now chemical process is obviously to do with breaking and making bonds. In this case, is going to be cracking. So you can crack longer hydrocarbon chains to shorter ones. So put cracking. Brilliant. Okay, so we get 2 marks for that. Obviously, you can probably see where the marks come from. I'll mark them up. You get 1 for that one and 1 for that one as well. Okay, right, on to B. So B, it says alkanes. Alkanes and alkenes can both be obtained from crude oil. It says explain why alkanes are unreactive. Okay, so All right. Okay. So, why it tends to be, or why alkanes are unreactive. So, just getting the lighting right there. Okay. So, we need to explain why alkanes are unreactive. So, the thing we need to say is that we have alkanes have this very non-polar structure, or the electronegativity difference between the carbons and hydrogens is very low. And really, for things to react, we need this polarity. We don't have this with alkanes. So there's one of them. And also the carbon-carbon and carbon-hydrogen bonds are very strong. And that makes it really difficult to break them. And so therefore it's really difficult for them to react with anything. So there's the two reasons there. So we're just going to write that on there. So we're going to put strong CC, or you could say CH bonds. And we can say that alkanes are non-polar. So again, we've got two marks there. So let's just mark them up. So we have one for saying we've got strong bonds in these molecules. It's better to specify as well. And the alkanes are non-polar as well. That is really important because that's one of the main ones there. Okay, right. Part 2. State the bond angles in a molecule of ethane. All right. So the bond angle is going to be ethane. This is a carbon with 4 hydrogens, so that's going to be tetrahedral. And ethene, so if I just draw it out here, ethene has this setup here. Now you can see this bond angle here, there, is going to be 120. So anything with that is going to be trigonal planar, and it's a flat molecule. Alkenes are flat, so that's going to be trigonal planar. There you go. So you get 1 mark for both of them. And then it says state the shape of each molecule in terms of the arrangement of the atoms bonded to each carbon. Okay, so the degrees, which is obviously how big this thing is, we need to say that ethane is 109.5 degrees and ethene is 120 degrees. Okay, so this is going to be, sorry, I put this in the wrong place. So the bond angles are going to be 109.5 and 120 for ethene, and the names are tetrahedral and trigonal planar. Sorry, I put that in completely the wrong place because I've been focused on there. So we just swap them 2 ones around there. There you go. Okay, so you've got ethane is 109.5, which is tetrahedral, and 120 is ethene. There you go. It's been a long day. Okay, right. Make sure you put them in the right place because the examiners might not give you the mark for that. All right. Okay. So IV. It just pays to make sure you're reading to this properly. Right. Okay. So IV. Explain why these molecules have different shapes in terms of the carbon-carbon bonds present. Right. Okay. So what they have is your ethane molecule, which is your 4 carbon bonds. So it looks a little bit like that. These have 4 single bonds that's attached to it, and the single bonds we call them sigma bonds. So we're just going to put 4, and that's the symbol for sigma. So the 4 sigma bonds on the carbons in ethane. And what we have in the alkene, if we just come back up to here, is we have the 2 sigma bonds. So we have them there. 3 sigma bonds. We've got 1, 2, and one of these bonds here is a sigma. And we also have a pi bond as well, which is part of this double bond. So yeah, you've got to be really careful that I don't say 2 sigmas, it's actually got 3. Because if you have a double bond, you have a sigma and a pi. So this one does have a double bond. So you've got a sigma there, and obviously the 2 standard sigma bonds. And you've got a pi and 1 pi bond on carbons in ethene. Okay, so there we go. Right, and then on to the next part. So this is C part 1. It says use a series of equations to describe the mechanism of the reaction of ethane with chlorine to form chloroethane and name the steps in this reaction. Right, whenever we're seeing an alkane reacting with a halogen, remember alkanes are very unreactive. And one of the ways in which we can actually make these react is by creating a really reactive species. And this would be through creating a free radical. And free radicals are created using UV light, and we shine the UV light at a halogen, for example, which is Cl2, and we get homolytic fission, which means the bond splits and we get an electron moving either side. So this is actually called initiation. So we're going to write that first step there first. So we take the chlorine and we're going to add UV to it, and effectively what we form is two Cl dot radicals, and this is called initiation. Okay, and then what happens is we then need to go into the next stage, which is propagation. And remember, the ultimate goal is to take our ethane, which is this one here. So we'll put ethane there, C2H6. And what this does, this always reacts with the radical from the previous step. So this is going to be Cl dot, which is there. And then what we form is, this is like a game of pass the radicals. So this radical then jumps onto the alkane, and the hydrogen is then passed over to form hydrogen chloride. So what we get is this, C2H5 plus HCl. Okay, this is the hydrogen chloride gas. And remember, the radical from the previous step will form the radical for the reactant for the next step. So we drag this radical down here. So this is going to be C2H5 dot, and that is then going to react with more chlorine that's unreacted. So that's this bit here. So that's the tricky bit. So remember, you've got to put that one in there. And then again, it's getting past the radical. The radical moves over to here, and the chlorine from here moves on to there. So ultimately, we now have our haloalkane, which is there, plus Cl dot. And crucially, the product here is the reactant in the first step. So it keeps going round and round and round until it stops. This is called propagation. All right, okay. So once we've, obviously this will keep going, we can have a final step, which is called termination. And that's where we have two radicals that collide. Notice these reactions here. In propagation, it's always a radical and a non-radical reacting together. If you see that, termination is always two radicals. When two radicals collide, they form a non-radical. So this one, it's saying we need to form chloroethane. So to form chloroethane, our termination step is going to be C2H5 plus Cl dot. Go. And that's obviously going to form C2H5Cl. And this one is called termination. There you go. Termination, obviously terminal to end, or terminator, or anything like that. Right. Okay, so this is five marks. So we have 1 mark here, 1 mark for this step, 1 mark for this step, 1 mark for this step, and then 1 mark for labeling each of the steps here: initiation, propagation, termination. So 5 marks, a good chunk of marks there. So that's good. Cool. Right. The last one, it says write an equation to show how butane could be produced as a byproduct of this reaction. Right. Okay. So butane is C4H10. So the only way in which we can make butane is by taking 2 of these radicals and colliding them together. So that's exactly what we're going to do. So we're going to take C2H5 and we're going to react that with another C2H5, and that's going to form C4H10. And there we go. There's our final mark. So 13 marks in total. On to question 5. Okay, so this is the final question. This is question 5. And it's probably a tough one as well, because it's talking about testing, chemical testing. A lot of people find this quite tough. So it says a hydrocarbon P with the formula C6H12 readily decolorizes bromine. On reaction with hot, concentrated acidified potassium manganate solution, a single organic product Q is obtained. Q gives an orange precipitate when reacted with 2,4-dinitrophenylhydrazine or to cut it short, there's 2,4-DNPH reagent, but there's no reaction with Tollens reagent. And so what it's asking us to do is explain these observations. Right, okay, so let's do this in a really methodical way. Okay, so the first thing is it's talking about that hydrocarbon P has the formula C6H12, is readily decolorizes bromine. So that's a classic sign of an alkene. So we're dealing with an alkene here for P. So we're going to add that in there. So we put in decolorization of bromine, of Br2. So that means that P is an alkene. Okay, right, so there you go. So that's the first one. And then it says, on reaction with hot concentrated acidified potassium manganate solution, a single organic product is obtained. Right, so what we're doing, your potassium permanganate is actually an oxidizing agent. So this double bond is effectively going to break. But we're only going to produce a single organic product. So what that means is that we won't get any cis trans. So we've got to have a molecule where I have no cis trans. And also we've got to be able to have a carboxylic acid being produced as well. And this can only be formed when we have a terminal carbon. So basically what we're trying to say is that the manganate would break the double bond. Okay. So that's going to be important. Now we need to think really carefully about this later on. Okay, so the hot concentrated manganate 7 VII. There's a bit of Roman numerals there. What this does, this breaks the C double bond C. Okay, so that's really important. That's what that does. But then it says that Q. This is actually what Q is. It says, so you formed your Q, and it says it gives an orange precipitate when reacted with 2,4-dinitrophenylhydrazine or 2,4-DNPH, but there's no reaction with Tollens, right? So the DNPH is testing for the carbonyl group. So that's effectively what we have. So we know we've got a carbonyl group. So we're going to put in there 2,4-DNPH. And so this means we have a carbonyl group, C double bond O. So we'll just put that in there, carbonyl group. There we go, present. And this is going to be in Q. Okay, so that's the first thing. But it doesn't react with Tollens. Now, Tollens will only test for an aldehyde. So if there's no reaction with Tollens, we know that this has got to be a ketone that we've actually got here. So we're going to put that there. So we've got no reaction with Tollens. And this suggests Q is not an aldehyde. So what it means is, because it does react with DNPH, we get this orange precipitate. It means the only thing it can be is it has to be a ketone. Okay, so we're just going to put that there. But your marks you actually get for this is 4 marks. So you just get a mark for identifying what each thing means. So 1 for saying what the decolorizer bromine does, 1 for the breaking of that double bond, and then 1 for saying that actually because of the manganate that we've actually formed our carbonyl. We have a carbonyl group in there, but that carbonyl is not linked with an aldehyde, so therefore it's going to be the ketone there. Okay, and the next one. Okay, so it says draw the skeletal formula of P and give its name. Right, so this could be a range of anything. And so what we're going to do is we're going to write down the different formulas of P. And remember, P can only form one organic product. It can't be an aldehyde, because we know that. So we know it has to be somewhere in the middle, the double bond. The alkene, sorry, so it has to be somewhere there has to be branching coming from it, and also we must have some kind of symmetrical some kind of symmetry, because we can't have any EZ. We only form one organic product. So we can either have a symmetrical molecule, or we have a secondary, or an alkene with a that's bonded to two other groups. So I'm just going to draw them out here, and we're going to name them all. You can pick any one of them. You only need one of them. That's written down here. So I'm going to start right over on this side. So we can have, now it is skeletal. So we literally just drawn the skeletal formula. So we can have this one, which is 2,3 dimethyl butene. Okay, you can have that one there, or you can have this one. That one there. We got obviously the carbon on the end, and that one's 2-ethyl butanone. Or you can have this one. So you can go down and along, and there's a double bond. See, it's all these are like secondary. Can you see here? So that one's going to be 2-methyl pentwanine. Or you can have this one, and we have a double bond again on there, but this time we have the 2 methyl groups coming from it. So that one's going to be 2,3 dimethyl butanone, which is that one there. So any one of these molecules here, you either have, you can see we've got the alkene is in the middle here. You can see there. There you go. There it is again, and there it is again. And this one is the only one with a bit of symmetry on it. Again, this wouldn't give any type of EZ, which is this one here, because we've got symmetrical molecules. So that's crucial, because we're only forming one single organic product, and that's the key thing here. Terminal ones here, terminal alkenes, will also do the same as well, because if you think about it, you'll have a carbon there on the end with 2 hydrogens coming off, and you can't have any EZ with 2 hydrogens on the same side like that. So that's why it has to be terminal alkenes that are on the end here. But crucially, we need to form a ketone as well, so we can't have the double bond there, because that would form an aldehyde, so it must be there. So that's why we have these options here. Okay, right, and then on to the next one. It then asks us to do the same again, but this time we're going to draw Q. Now we know Q is a ketone, and I'm going to link them to these molecules here. So if you've drawn this one, you need to draw this. Effectively, this bit here breaks off this bit, and you have your oxygen on the end of there, so it effectively splits. And this is called, I'll write all these ones out, because this won't take too long. So this is propan-2. If you drew this one, you can have, obviously you're going to form this, and there's your ketone there, and this is pentan-3. There you go. If you drew this one, you're going to form this. I think you're probably getting the gist of this now. There's your alkene. There's your ketone, sorry. This is pentan-2. Okay, and if you drew this one, then you're going to form this. There you go. And that is 3-methyl butan-2O. All ketones, including that one as well. So they're all ketones, all of these. And you can see that probably the most common ones will be these ones that you may be thinking of. So they're all ketones, which is obviously very important, but crucially you only form one of the products, which is this one here. Okay, so you get 2 marks for each one of them. So the marks come obviously by drawing the structure, and then one for naming it as well. So there we go, and the names. So you only need one of them though, you don't need to draw all of them, it's just one of them. So you get the 2 marks there. Okay, right, so on to the next one. There we go. Okay, so it says there are several structural isomers of P that also decolorize bromine. but only 4 of these structural isomers exhibit geometrical or cis-trans isomerism. Give the structures of any 3 structural isomers of P that exhibit geometrical or cis-trans isomerism. Right, so all we have to do is just obviously use the same formula, which is a P. Remember, P was your alkene, but we have to draw them this time where we do have your geometrical isomerism. So the other ones we had to draw them where we couldn't get that, but this time we are. So they're looking for 3. So we could have, what I'll do is I'll draw the formulas, I'll draw out both formulas actually. So we could have something like this, which is C2H5. I find easier is if you have your 2 carbons there, if you just isolate that bit there, and you could have, you can see here you've got a hydrogen, a CH3, which is there, and this one you've got a CH3 coming off there. I can have C2H5, so that one could work. You could also do this one. So all you're doing really is just drawing CH2, CH2, CH3. All you're doing is you're just drawing basically different forms of this molecule here. So we're going to put hydrogen there, CH3 down there, hydrogen, and this one's going to be CH2, CH2, CH3. You can see this is geometric because this doesn't rotate, this double bond, but when it's made, it's fixed in this position. So you can see here that the 2 hydrogens here are on the same side. So this one here, these ones, the CH3s, are on opposite sides here. So this would be trans, and this one would be cis. So you're looking for the 2 groups here. So yeah, that's that one. And you can do this one, CH3, CH, double bond, CH, CH, CH3, 2. Okay, so let's draw that one out. So we've got our carbon, hydrogen, 2 CH3s coming off there, and then a CH3 off there. See again, that one is cis because the 2 hydrogens are on the same side. And then let's draw one more because there's only one more for this one. So this is going to be C2H5, CH, double bond, CH, C2H5, and the molecule will look like this: C double bond C, hydrogen, hydrogen, C2H5. There you go, and then C2H5. There you go. So again, this one could be this one is cis or trans. What you can't have though, if this was on the end like in the previous ones, if you had 2 hydrogens here, that wouldn't provide any cis or trans. So obviously that's obviously quite important to make sure you've got that bit right as well. So these ones are always in the middle, and that's what makes these slightly different. So any one of them 3, any one of them 4 should I say, so you only need 3 of them, would get the mark. And so that's it, that's the end of the paper. I hope you did well on the paper, and keep up the hard work. That's it. Bye bye.